Now that we've looked at the basics of Voronoi fracturing and some more intermediate techniques, and we have our geometry ported over from Maya to Houdini, let's look at a more advanced and realistic fracturing setup. This is something that I'm pretty proud of. It's a technique that I've developed that I haven't seen used by any other artists or any tutorials or anything. It's kind of sort of my signature thing, and I think it'll be really useful for you as well. This uses some manually specified cutting geometry, so at first glance it might look like we're setting up a Boolean operation, but what we're actually doing is very accurately art directing exactly where we want our detailed Voronoi cracks to be. Before we start setting up that fracture, let's just make one quick adjustment to the render cam that we didn't make when we first brought it in. You'll notice that this isn't quite HD aspect ratio. If we dive into the render cam, this will have some resolution settings on it. And right now it's set to 1280 by 853, but the actual resolution that we'll be rendering at is proper 1080p HD. So it's 1920 by 1080. And then this should match what we've originally set up with our animation in Maya. This is our final output resolution. It's very important to keep the frame in mind when we're setting up our fractures, because we're going to want to compose the fractures, with nice image composition in mind. Now let's go up to our top object level and start setting up our fracture. If we go into the tower node, we can find our unbroken piece of helipad geometry to start fracturing it. That's the original piece that we blasted to get it out of the way here. Originally, we just quickly selected it and blasted it away by its primitive ID, but this time we're going to isolate it using its actual proper path name. Now if we right-click on our Alembic node here, and let's look at the path. If you scroll to the bottom, you'll see an object called helipad unbroken full helipad unbroken full shape. So we can use that name to isolate that and start working on it. Let's drop in a blast node and connect it to our tower Alembic file, not these blast nodes. And if we view it, let's back off a little bit from our render camera and just work in our perspective view. You'll notice we don't see the tower anymore because we're not viewing that Alembic node. Let's also turn on our wireframe on shaded view to make things a little bit more visible. So yes, if we display this blast node, we can isolate the unbroken shape by typing @path for the path attribute equals star helipad unbroken star. So this will delete anything with helipad unbroken in the path name. So now if we tick on delete non-selected, it will only leave this helipad unbroken shape. And now for easy referencing, let's use a null node that we can always point to access this shape. You'll be using null nodes a lot just to create access points to easily merge in objects and reference them and to know where to find them. So we'll call this out helipad full. But for visibility's sake, we can leave our visibility on the blast node here. Let's call this, let's make another null node and call this out tower no helipad and display that. So if we go up top, we can turn off our tower anim because we don't need that piece right now. And let's create a new geometry node and call this fracture. Then go inside this node, delete the default file, and we will object merge our full helipad in here. Let's add helipad to this name to keep everything clean. And now we can start planning out some fracture lines. Let's go to the frame where the robot first contacts it. Right about, it starts contacting around 1050 it looks like, but we get more full contact right around about 10, yeah, we'll go 1060. It doesn't have to be exact right now. This is just for fracture placement. Let's go back up to the top object level and turn off the background buildings because we don't need to see all that. It's a little bit distracting. And back into our fracture node. And we can start dropping in boxes or grids or spheres or any other geometry that you want to use to specify where the helipad will be cut up. I'll start by dropping in a grid here. And I'll leave it at the origin and connect a transform node. Now let's right click on our object merged helipad, pull up the spreadsheet to see the point position of its packed primitive, which should be the centroid of the object. Now if we go to our transform node, we can put that value in to our translate here to get it in the right ballpark. It's 586 by 32,092 since the skyscraper is absolutely huge. We can close this. And you'll notice this transform manipulator is up at the centroid of the object where we've specified this transform node to go. Let's control click to template the helipad and put our display on this transform node. We'll pull that up a little bit. And it's super tiny, you can barely see it because we're working at a pretty mega scale here. So even dragging your uniform scale up to 10 is not going to be enough. Let's scale this up to 100. Even that's not enough because this thing is huge. We've got some seriously massive robots here. Now let's change our grid orientation to the XY plane, that'll do. And go back to our transform node here. And we can use the regular scale parameters to make this a bit bigger. And we'll shrink it in Y because it doesn't need to be so tall. And let's rotate it to match one of the arms here. So just to take a step back for a second, when we're plotting out our fracture lines, it would make sense, given how these big heavy robot arms are landing on the geometry here, we might expect some fracture lines to emanate out in the same direction of the arms. Certainly we'll want it broken up into smaller pieces there, and some slightly larger pieces as it spreads out. But we want these arms to be the central impact point. Looks like we're also getting quite a bit of impact with the chest here. That's really digging into the geometry quite a bit. So we'll want a bit more geometry cutting this up, and we'll kind of spider web it out from there. Also, if you remember from the intro video, we mentioned that we're going to be pre-damaging this geometry a bit before the robot even hits the thing. This helipad gets pretty decimated pretty badly from the robot's impact. The entire half of this thing gets torn off, which might be hard to justify such an extreme amount of destruction from its impact. But if we pre-damage this thing, it'll give us some really interesting visual detail before the robot even hits it. And it'll also help to explain that this thing's already been damaged and beaten up, and it'll make a lot more sense for it to fall apart with some extra impact. So I'm thinking the camera is around here. if we take out some chunks from, let's say, this section, we'll take out a few visible chunks here. Let's actually go right to our render camera so that it's not guesswork. Let's back up a bit. Yeah, taking some chunks out here, maybe a little bit there. We want it distributed kind of randomly across the geometry so it doesn't seem too perfect, but you can use your own artistic judgment where you want to create some pre-existing damage. I would just say that since if we go to the end of the shot, you'll see that it's going to be fractured right along here. It's hard to see with our full helipad in the way, but if you'll remember, there's a little bit remaining here, so it's getting broken across somewhat evenly. So if we can take out some big chunks on either side here, approximately where that is, that'll help to justify the damage. So if we get out of our render cam again and go back to our main impact frame of 1060 and redisplay our transform node and template our helipad, I'm going to rotate this to match up with his arm. And we're going to make sure this goes all the way through the bottom of the geometry. And this will be a good starting point for a good initial cutting spot. You can probably imagine once you start adding a lot of these cutter geometries, this could get really visually cluttered and difficult to see what's really happening. So let's add some extra nodes to help trim things down and make it less visually cluttered, and it'll help us to provide some cleaner input into our fracture setup. So one node that I use an awful lot for this sort of thing is the simple clip node. If we wire this in after the transform and display that, this clip node gives an origin point and a direction for it to clip all of the geometry either above or below that defined plane. So if we use the same transform values here, we'll copy the parameter in our transform and paste the copied values into our origin. You'll notice that that's by default cutting things below the plane. Let's change that to keep the primitives above the plane. I'm sorry, it's already keeping primitives above. We want the primitives below. My mistake. Let's move this up just a little bit. And let's duplicate this, the clip node that is. And for the second clip node, we want to keep only the primitives above it. But then this one will move down a bit, so that it's really isolating just what we need to see to help see where these fracture lines are going to be. Now, obviously we don't want this fracture line to be so perfectly straight and just running straight directly down this path of this grid. So let's start adding some noise to our cutter geometry. We're manually specifying the geometry to use, but some procedural noise will really help to give it a little bit more of an organic look. I usually use a simple mountain node to noise up my cutter geometry. So if you add that and display it, the default height is not going to be nearly enough, especially at this scale. So if we start cranking this up, we can really use quite a bit of noise here. This is probably not going to be enough geometry detail to give us all the detail we need. So if we go back to our grid, we'll want to increase the number of rows and columns. Let's increase the rows a little bit and the columns a little bit as well. So now we're getting some much more jagged chunks here. We'll also want to make, that's probably a little extreme. Let's Let's dial down the height of our mountain. That's pretty extreme there. And we'll also want to make some more curved shapes with this noise. So we'll want to lower the frequency. Oftentimes with these frequency settings, I will copy parameter on the first, the x value, and I'll paste copy relative references to second and third values, so I really only have to worry about changing one of them. Now if we change the frequency to about 0.001, you'll see we're getting much softer curves instead of just absolutely random looking points. And now that we have these softer curves, we probably will want a little bit more height on this mountain here to make that a little bit more extreme and get some more curved lines. And then we'll probably want to adjust the transform now, since that doesn't follow our original geometry very exactly. This can be a little bit time consuming sometimes to line up all these cutters, but in my opinion the manual control of where your fractures are going to be is absolutely worth the time spent placing these cutters. I've also at times generated some procedural cutter planes, so we can experiment with that a bit as well. And that's fairly easy to do, but of course that doesn't really give you all of the control to have all of the cuts happen exactly where you imagine they would given your current fracture locations. So that's a pretty decent spot for one fracture line. If we look back at our render cam, it'll be a pretty interesting path for it to follow. And now that we've got this lower resolution noise added, let's add in one more higher resolution noise to add a little extra detail here. So in order to do that, let's go back to our reference frame again, and let's subdivide the surface a little bit, because at our current geometry resolution we're not going to get a lot more detail in the crack path. So with a subdivide node, we can increase the depth once or twice. In this case, let's increase it to 2. And I often use creasing to keep the same general shape. It's really up to you if you want to keep these really curved shapes, or if you want to increase the crease to to make it more jagged as it was originally. And then now that we have this extra detail, we can add another mountain node. Actually, let's copy our last one and pipe it in here. So that is, by default adding some more low frequency noise to our cutter planes. But we want much higher frequency now for this one, just for added detail. And this height, because we're adding more fine detail, is going to be way too much. Let's dial this down and increase our frequency some more. These values are pretty delicate at this scale, since the scale of the skyscraper is so huge, and we're working with such small frequencies, or such low frequencies, to get things to read at this scale. It's kind of delicate adjustments on these noises here. That looks pretty good, and we'll increase the height a bit to make it a little bit more erratic. And set our display node to that mountain. So now you have a pretty jagged, curved path. And this will come in handy once we start scattering some more Voronoi cutter points along here. One more note, sometimes this can be a little bit messy when the geometry kind of folds over horizontally here. One way to clean that up a little bit is to reduce the grid resolution vertically. So we can either scale it in the transform node, or we can reduce the resolution of the grid itself, or any combination of the two. In this particular case, I'm just going to scale the transform in Y. So it's much lower resolution, and it's not folding over itself nearly as much as it was before. And also, let's move these clip nodes to happen after the noise operation. So now the result of this is a much cleaner fracture line without all of the weird overlapping we were getting before, because that can it can be okay, but it could also interfere with our Voronoi results a little bit. Now let's adjust our transform node a little bit more. We'll grab our manipulator tool, and deselecting the transform node will get that preview geometry out of the way. Let's move this back to where the arm is, and it's going to be a bit less precise once we have all this noise applied to it, but that's really okay since we don't need to be super precise about the locations as long as we're guiding it to be roughly in the right place, because there is some chaos in these natural fractures. And I think I will increase the height of this low resolution a little bit more, just to curve that path a bit more than it is now. Okay. Before we get deep into the implementation of this geometry-based Voronoi fracture, let's add one more cutter plane along this primary fracture line right along here. That's a superhero fracture point and will help illustrate our cutting. Also, we'll notice that this one doesn't go all the way through the other side of the surface. Sometimes that's okay, sometimes it can be a little bit messy. That means you'll get, it won't actually cut the piece because this will all be one chunk. But, for our purposes, we'll leave it as is for now. And let's copy this transform node and paste it back. And let's add a merge before the mountain node, so we can combine multiple cutter planes before we use it to cut the geometry. So for this one, let's do a simple y-axis rotation. That'll do. And we'll shift it in X to be approximately where our rough animation fracture line is. In our case, we don't have to stick exactly to where our rough fracture line is, but we'll want it to be pretty close. So now this should give us a pretty interesting shape for our initial fracture test. Let's create a subnetwork here, and if we connect our geometry that we want to fracture, the full helipad, into the first input, and if we connect our geometry that we're using to cut this into the second input, then we can implement our actual Voronoi fracture in here, and we're pretty sure we're going to want to use the same subnet to cut some other pieces of geo. So building it in the subnetwork will make it easy to cut and paste and use in other networks. Now that we have our input set up, the first element of the Voronoi fracture is to scatter points along these cutting planes that we've defined. So if we drop in a scatter node and connect our second input to that scatter node, you'll notice that our visibility isn't reflecting what we see here, because I've pinned my visibility using this pin here to view at the fracture level. So if we unpin that, then we can see what we're actually currently looking at in our network here. So I've scattered some points along our input cutter planes. It's a little bit sparse right now. We will actually need a ton of these points here. It's defaulted to 1,000. Let's turn that up to 10,000 points. And the next element that we'll need is to scatter points in the geometry that we're piping in here. So let's actually create a VDB based on the geometry that's coming in. So if you type VDB from polygons and connect our first input, look at what that gives us. And actually I'm going to cancel this. You have to be a little bit careful with some of these volumetric defaults. Some of them are set to be pretty high resolution by default. Right now we have a voxel size of 0.1, and since we're dealing with a skyscraper thousands of units tall at a pretty big scale, this is going to be way too huge. I'm going to turn this up to 100 just so it doesn't kill us by default to create this initial VDB. Now if we look at the scatter node, we have all these points available, and let's convert those scatter points into a VDB as well. In this case, we'll use a VDB from particles. And if we pipe the scatter points in, you'll see that that creates a VDB. Once again, we have to be a little careful of the defaults because it's only 0.1. Let's turn this back up to 10. And right now we don't see anything because our point radius scale is pretty small in relation to the overall scale we're dealing with. If we turn the point radius scale up to 100, which is pretty large, you'll actually be able to see a result here since the scale is so massive. That'll actually be decent for our first initial test, and we can use a combination of these two VDBs to define some of the scatter points that we'll be using for our fracture. So we'll need, in addition to these cutter points scattered here, we'll need some additional points inside those cutter planes to define those large chunks. You'll see in a moment why these scatter points alone will not be enough to define the chunks. So if we drop in a VDB combine and we pipe in the two VDBs that we're using so far and visualize the output of that, you'll see that by default it's just giving us exactly what our first input is, the helipad VDB representation. So the operation on the VDB combine is set to copy A, just grabs the A input. But if we set this to an intersection of the two, it'll only give us a volume where the VDB for the helipad and for the cutter planes intersect each other. Now let's go up to our top level node and let's hide our tower for now, just to keep our viewport a little bit cleaner here, and go back into our subnetwork. Now we can use this to help specify Voronoi points only where we need them. In order to scatter points all through here, we'll need to convert this to a fog volume. So if you type in convert VDB and pipe that in here, we'll want to convert this to a VDB, even though it already is, but the VDB class will be SDF to fog. So that'll give you results similar to the ISO offset that we've looked at before. Now this, if we drop in a scatter node and pipe that fog volume into the scatter, you'll notice that it's scattering points all throughout that intersection area between the two. And also for this, we'll need a fair number of points. Turn it up to 10,000 for the moment. And we can compare that result to the scatter points from our VDB cutter planes themselves. So actually, let's increase the scatter points in the fog volume up even more. Let's do 3 times as many. Let's do 30,000 of those. It's quite a lot of points, but we will be removing some of those. Now this setup leverages manually specified cluster values to define our specific cutting areas. So let's start applying those to our various scatter points. So let's reorganize our network a little bit here and drag the cutter plane scatter node off to the side. Then let's drop in an attribute create node to start specifying our cluster values. On the cutter plane, let's initially create an attribute called cluster with a value of 0. That'll be fine for now. And we'll call this node attribute create cluster. And if we copy this, we can paste a copy underneath the VDB scatter node and set these points to a cluster value of 1. And then we'll want to do an attribute transfer between the two. So if we drop an attribute transfer node, connect the VDB scatter points to the first input and the cutter plane scatter points to the second input, that'll transfer cutter plane values to the VDB scatter point values. We'll visualize that and disable all of the primitive attributes. The only point attribute that we want to copy over is cluster. Now the output of this attribute transfer node is just going to be these incoming VDB scatter points, not including any of the cutter points, and some of those will have picked up the 0 value from the cutter points rather than their default of 1. You can see that in the spreadsheet here. So if we drop in a blast node, we're going to blast away any points that have picked up that value of 0. So in the group for the blast node, we'll use our attribute query shorthand at cluster equals 0. Now if we middle mouse on the blast node, see it's 30,000 points, which is the same as the 30,000 points in the attribute transfer. So it hasn't deleted anything. Sometimes nodes that have a specific group type will need to have a hint specified so it knows what type of group it's dealing with. In this case, if we set it to points, then Houdini will know that this is referring to a point attribute, and you'll now see that it is leaving behind 28,000 points instead of the 30. It's actually deleting the points that it found with a cluster value of 0. So right now it's not transferring the value of 0 to very many points. We'll have to increase our distance here so that more points pick that up. So if, let's say we use a distance of 50, then we're down to 10,000 points here. Let's deselect our attribute transfer node. That can trip us up a little bit because Houdini can show a preview of any nodes that you have selected. So we didn't notice that it deleted more points until we deselected that attribute transfer. So you notice that this is deleting out more and more of the points that are close to that original cutter plane and the cutter plane scatter points. Let's delete out a little bit further for the sake of this illustration. Let's delete out 80 units. And that's getting rid of most of the points that we have here. So we may need to increase the size of our VDB buffer. So if we go back to the VDB from particles node here, then we can increase this point radius scale a bit more. If we turn it up to 120, for example, it'll create a slightly wider buffer. 150, we'll make it wider still. And for this illustration, let's take it all the way up to 200. So now we have 13,000 points left over from our VDB scatter. So now we have two different sets of points that we're working with. we have these points in the VDB scatter that are going to outline our large chunks of geometry. And then we have these cutter plane scatter points that are going to split in between the other scatter points that we've specified. So if we merge those together, and then we'll drop a color node and connect that to our merge, we'll do a random from attribute and specify the cluster as the value, as the attribute that we're using to randomize our color, and this will give us a nice visualization of how things are being chopped up by default. Now, before we run our initial Voronoi fracture, there are a couple more steps we'll have to take. This geometry that we originally brought in, if you'll remember, is packed geometry, that tower helipad there. This packed geometry doesn't give us direct access to all of the points and primitives that make up that object. Right now, we only get a single point and a single primitive. But we'll want to expose all of the faces and points of this geometry as if it were normal geometry. So let's drop in an unpack node. This will, if you middle mouse click on it, you'll see that it's no longer packed geometry like our original geometry is. But you'll also notice that we have all of our points here, but we still only have one primitive. So this primitive is this polygon soup here, and we'll have to convert that polygon soup by dropping a simple convert node, and we'll convert it to polygons. You'll notice by default it's converting that to polygons, and if we middle mouse click on it, now you'll see all 3,280 primitives that make up this geometry. So now we have direct access to all of that. There's not much in the way of attributes on that, but you can see all of the numbers for all the faces that exist on it. So now that we have access to all of that geometry, we can go back into our subnet here. And actually, just for our initial tests at least, let's turn down our Voronoi points a little bit. This is a little bit heavy for our initial fracture. So if we go to our scatter node for the isosurface, let's change this from 30,000 down to, we'll say 15. And let's turn down the cutter points from 10,000 to 8,000. So that'll be a little bit more sparse. If we look at our color feedback, you can see the different points there. Now let's create a Voronoi fracture node. Pipe our points into the second input, and we'll pipe our geometry from way up top. Our input number 1, we'll pipe that into the first input of our Voronoi fracture. Now, since we have clustering set up on this object, we'll go to the cluster tab and enable cluster pieces. We don't want any noise on it. We want to use our raw values as they are. And we'll make sure that this cluster attribute called cluster is the same attribute we've set on our points. So now that we've set up all of that, let's display our Voronoi fracture and see what our results are. Once our fracture has finished processing, we can drop in an exploded view node to get a better look at the results of this. Let's check it out. So now you can see how those cutter planes that we've placed through the object have severed it into really interesting looking pieces. It's much more a realistic and organic edge than most Voronoi fracture setups will give you. However, you'll also notice that the output isn't as clean as we'd like, and this is something you'll run into an awful lot. Although we're liking the general shapes that we're getting out of these cuts, these inner pieces should all be one piece, and because we use the same cluster value for all of our inner cutter points, so we shouldn't be getting a ton of different pieces, nor should we be getting some of the holes that you're seeing on the inside of this geometry here. This should all be a pretty, pretty noisy but complete hole-free surface here. So we're going to do a little bit of debugging to figure out why we're getting some of these slightly buggy results. There are a few things that I look for when I have some problematic fracture results that I want to debug. First and foremost, you always want to make sure that your geometry is a fully closed surface. It doesn't have any holes, and sometimes these holes aren't very obvious. Sometimes, even if the surface looks very clean and nicely connected without any visible holes, sometimes you'll have overlapping points that aren't actually merged together and little problems like that. One way to check for that is to group the geometry and go to Edges and enable that. Let's disable the number option. And under Edges, let's tick Unshared Edges. So if we connect that to our geometry and display it, you'll see that there are 0 primitives in group 1. Actually, let's also make sure that everything here is set to edges. The entity will be edges, and still there's 0 edges in group 1. Previously it said primitives because we were creating a primitive group. But if you have some edges that are part of a hole in the geometry, then this will detect those edges and highlight them for you. But that's not the problem in our case. Another thing I'll often do is I will drop in a clean node. And I remember one case recently where I had a polygon or two that had a reversed orientation, and I was able to fix my fracture problems by turning on orient polygons. And really, sometimes it can turn into a little bit of a time suck to diagnose your fracture issues, and it's an unfortunate difficulty sometimes, but the more you do it, the more you'll learn to avoid the problems, and you'll learn what the common problems are. Sometimes in this clean node, I will start turning on, a whole bunch of options just to see if that fixes our results, because any number of geometry issues can cause fracture problems. But in this case, running a clean node on our fracture didn't help us out at all. I'll also sometimes use a polydoctor node. This one is a fairly robust tool to fix some similar and some different problems with your geometry. But still, none of these options in the polydoctor were able to help out in this case. And then I was thinking about the sheer scale of our scene. Oftentimes in Houdini or any other 3D software, whenever you're working at an extremely large scale, you can run into precision issues with computations. It can cause any number of really bizarre problems, from display issues to actual, incorrect results. So our skyscraper is around 32,000 units tall, so I figured I would give a shot at transforming that geometry down. So if we go back into our subnet with our fracture setup, let's set our update to manual so that it's not trying to cook all of the time. And underneath our input geometry, I'm dropping in a transform node. And this transform node, it has a default value in the pivot of the centroid of the object, which 95% of the time is what I want on a transform node. But in this case, we want to scale everything toward the origin. And let's try scaling it down to 0.1, to 10% of the size that it originally was. Let's make a reference copy of this transform node. So if you right click on it and go to Actions, Create Reference Copy, What this will do is it'll create another transform node that's referencing the values from this one. So anything you change in this transform node will be reflected in this one as well. And the reason we're doing that is so that we can put it under our input cutter geometry to make sure that that's scaled down as well. So now if we visualize our input geo and the template on the cutter geo, and let's turn our update back on, and let's space G in the viewport to look at that. It doesn't look any different, but if you check out our spreadsheet values, you'll notice that these are much smaller in size. This is only 3,227 units, so it's a much smaller range than when we're at 32,000. So this will affect some of the other settings that we originally set up. Some of our settings are size-based, so you have to be fairly careful when scaling this setup for different cases and different geometry. So if we start tracing through our network, we can easily identify those. Our VDB for our helipad surface is much too low res. 100 voxel size worked before, but now let's go down to, let's say, 10. And similarly with the VDB from particles, that's totally wrong scale-wise. So let's turn our point radius down to 20 and voxel size down to 1. Basically, since we scaled our whole scene down to 10%, these size-based settings I'm also scaling down about 10% as well. It seems to be scaling pretty well. It gives us pretty similar results as we had before, just at a different scale now. So now, if we look at the volume points, the point count isn't something that tends to be quite so scale dependent, so that can be left as is. And let's look at our merged points and our visualized points. Oh, I'm sorry. One thing you're noticing here is all we have left after we merge our points together and visualize them are the cutter points. Because another one of our distance-based settings is on this attribute transfer. It's looking for any of the helipad points within 80 units, which is far too large now. Let's turn this down 10% to within 8 units. So now we have all of our settings scaled down to work with the smaller helipad. And now when we visualize the Voronoi fracture, we should have some much better results. Now I'm cutting out the processing time from the video so that you don't have to stare at this as it computes the Voronoi fractures, but my fracture times are only about a minute for this so far. Of course that'll vary depending on your machine and the specs that your machine has, and probably some other factors as well, but this shouldn't be too terribly heavy. And in any case, let's look at the results of our fracture now. And this is much, much better than what we got before. So all we've changed is that we've scaled down our objects and scaled down some of our size-based settings to match. So this gives us exactly what we were expecting. We have our cutter plane geometry as one clustered chunk, which is splitting the helipad into a few other chunks. Much, much better. We can turn off our wire shaded view and only go to smooth shaded. And you'll notice that when you're up close, this is, it looks a little bit geometric on the insides. We've added no interior detail at this point, but I often don't need to add interior detail for some of these shots because we're using a fair number of Voronoi points to achieve these cuts, and once you back off a little bit, especially as we start adding in more and more cutters, some of this detail starts to look pretty natural, especially for something like concrete. Of course, this looks a little bit weird having all of our cutter lines combined as one solid object here. That's not a natural looking result that we'd expect. So the next step will be to break that up into discrete little pieces. And there are a few different ways to do that. You could apply some noise to the points for their cluster value. There are a whole handful of ways of manipulating cluster points. But my favorite method is to start by scattering some fresh points on our cutter geometry. So let's move our cutter input over a little bit here. And let's create a scatter node. And on this scatter node, we don't need too many points. Let's start with 100 points, just to begin with. So for all of these freshly scattered points, we're going to set a unique cluster value on each of them. So let's use another attribute create node and create an integer attribute on the points called cluster. And for this value, we're going to use the point number plus 10. The reason we're adding 10 to the point number is, if you remember, our cluster value of 0 means non-clustered, and the cluster value of 1 is reserved for specifying the large chunks and carving those out. So all of our cutter pieces, if we start with the value of 10 and upwards, then that's going to put all of those safely in a range that doesn't conflict with our other reserved numbers that we're using. So if we look at our spreadsheet, and all of these cluster values range from 10 up through 109. Now we're still going to use the more heavily scattered points on the cutter geometry to actually do the cutting, but we're going to change the cluster values on the point cutters. So let's do another attribute transfer and drop that in underneath these cutter points. And in the second input, let's pipe in our more sparsely scattered points with the unique cluster values. We don't need to transfer any primitive attributes. We're only transferring the point attribute cluster. Now we can delete the other cluster attribute creation node that we were using that originally was setting it to 100 for our previous version. We won't need this anymore. Let's drop in a color node after this attribute transfer to see what we're getting. Once again, we're going to use a random from attribute and set that to cluster. So now you can start to see how the points that we've scattered on the plane are transferring their values to these color points. Now it's not transferring the cluster value far enough to reach all of these cutter points, so we're going to need to increase our distance a bit. Let's go up and up until we totally remove any of the missing points. It's not a problem if you turn this up way too high, because it's just going to grab the nearest value. You'll notice after a certain point that it has no more influence. So as long as this distance threshold is high enough to hit all the points, you're in good shape. So now we can go back down to our Voronoi fracture node and look at the results of this. Once our fracture is finished processing, you're not going to notice much on the object here since we're in smooth shaded mode, which is actually pretty awesome because that means we're getting super clean fractures. Some fracturing techniques aren't very good about keeping a seamless surface. I know, especially with VDB fracturing, seams tend to be a problem, and many fracture techniques don't preserve the surface quite as nicely as just some clever Voronoi fractures do. Let's go back to our wireframe mode and look at this exploded out. Now you'll notice that instead of having one solid piece all through here, now we have lots of little pieces that are splitting up the big chunks of the helipad that we were shooting for. And if we go back to smooth shaded, we'll see how some of that detail looks without being biased by the wireframe. So we're already getting some pretty cool results, and from here it should only get only get nicer as we start adding in some more cutting areas. However, just judging by experience, anytime you have a large solid block like this, and if you remember, our camera's going to be right up close here, so these large pieces are going to be one solid chunk kind of falling away from the camera, and that doesn't look very good. It doesn't look like realistic construction. We wouldn't expect the entire helipad to be composed of one super thick block of concrete or any other material. So anytime we have a large piece of geometry like this, we're going to want to carve it out a bit on the inside. I know this particular section has been pretty long, so we're going to save the hollowing out of the helipad and a couple other little tweaks on the setup for our next video, also this week, and hopefully that'll prepare you for doing your homework and starting to carve up the geometry in the shot.